All right, can you hear me? Yes, thank you. So first, I'm very happy and honored to be able to come here to speak here and celebrate Richard's birthday. So people know me, know kind of I love parking function and have played with it for a long time. And it's all started with this. This is a picture taken at a conference in 1996, which is Rota Fest, the celebration Rota's 64th birthday. And you can say I think very tired this year. That's me. This is Giancarlo Rota, and I can see a lot of familiar faces. For example, Jim is here. I think Sergey is somewhere in the picture. Maybe you can find yourself. So this is the conference that Richard first talked about parking functions, and which I learned the parking function. So to be fair, parking function was not invented by Richard. It's like invented by Cole and Weiss in a paper in 1966. And it's starting from defining some random parking function. And at the beginning, it noticed that those things have bijections with labeled trace. And the cycle bijections is definition, including that also has one of the bijection, a very beautiful one, in the second volume, in the solving volume of the art of computing. But I think it is fair to say that the subject was revived by Richard, starting from a series of works he has done in the middle of 90s, including this is the first one I heard him talking in that Rota Fest. It's about hyperplane arrangement and relations and for the parking function. And I guess I write down to the data because this is the exact description Richard gave as what is a parking function in that paper, and as well as what I believe is the exact wording he used in his slide on that day. So I'm not going to read the whole thing. It's just that the parking function was introduced as a parking process and cars entering on a runway street with space one by one, and each driver before entering has a preference. So the rule is they enter the street, go to the preferred space directly, and park in the first space available from that spot. If anyone cannot find the spot, the parking fails. So parking function will be a sequence of preference so that all the drivers can park. And of course, if you don't need time checking a sequence to work that parking process, need to give some like a more precise definition. And Richard like to give a couple, several, I think, in his talk. And this is my favorite. So this is in terms of non-decreasing arrangement, or in other terms, all the statistics. So you give a sequence of integers. By the way, I heard from Adam that it's kind of computer scientists like to index things from 0 to 1. And it actually fit my purpose well. So all my things, I'm allowing to take values from 0, and my sequence is indexing from 0. So anyway, given the sequence, you just take the non-decreasing arrangement from small to large. And the sequence is a parking function if and only if the ice curve, as all the statistics, is non-negative and strictly less than I. So here's some examples. Well, a special case is increasing parking function. As the name suggests, that's a sequence which is a parking function and which is weakly increasing. I guess a suggestion that every comp will have a proof. And this part is my single proof on the number of increasing parking function is given by the Carter number. Well, it's also known the parking function is given by the K number describing how many labels are there. But I want to give you this proof, which is really not a proof, but just a way to represent increasing parking function by example, showing by a picture. So here is how you do an increasing parking function. If you about the sequence, what do? Do a picture for it. So on the like this is imagine this is the first quadrant, and beginning from the origin. Think it's 0, 0, 1, 4 as 4 vertical steps, and you want to put them at the x coordinate 0, 0, 1, and 3. They just connecting them by the horizontal lines to make a line pass. The condition of it as a parking function exactly means is a Catalan plus staying on or above the diagonal. So Catalan. The picture will show up again, so remember this. Okay, there are many possible generalizations of parking function. I think the most naive one is the vector parking function. Well, it has various names like X parking function, X equal parking function, but I think it's fair to say it's a vector form. So the definition is here. Take a non-decreasing sequence of non-decreasing integers. If you want to restrict to length n, you take n number, then so use our vector. So a new parking function of length n would be a sequence of non-negative integers, so that the ith order statistics is strictly less than ui. The comparing the definition using the classical case, we just define corresponding to this standard form using the standard case and report, etc. In Richard introducing those results in the middle 90s, he also gave several connections between parking function and the generalizations like hyperplane arrangement, non-crossing partitions, and partition interval order and some symmetric function, where actually things show up is like it's not the classical one, but some generalized parking function where that vector U is arithmetic progression. Also in a paper by 2002 by Jim Pittman and Richard, they defined introducing a vector. This vector general form of parking function. Richard's notation is slightly different than mine, which he called the x. The vector is x, the mine is u. And I don't change that one because his x is not exactly the same as my u. The equivalent x is basically the difference vector of the u. So there is a twist, though I keep the notation different. But anyway, that's still equivalent. And this number is the number of vector parking functions. And what Richard has is this is a polynomial in terms of those numbers u0, u1, etc. It's tell you how to calculate. It equals the volume of a special polytope. It's called a parking polytope, and which relates to order statistics. So, and it can be computed by a formula stat, which is kind of things relating to order statistics. People know in people already know. So what's next? So this again might get me interested because I want to count, right? So the first thing, whenever you have an object, you want to count how many are there. So my kind of goal is to count the new parking functions, and I like containing two steps. Well, except you didn't put them in that order, but there are two things: increasing parking function, and then take a permutation of all those terms. You got all possible parking functions. So Richard already has it as a polynomial in those fields. So what I'm wondering is which polynomial. Turns out it's a polynomial that already showed up in works when with the people working on approximation theory. And this is relating to a particular interpolation problem called the Shankar interpolation. So let me tell you what that is. So now we go to a little bit to the activation. So define what's the Shankar interpolation. Now imagine it's on the real line. You take n+1 points, called a0, a1 up to an. And in your mind, you can think of arbitrary the fixed numbers b0 up to bn. So what you want is a polynomial of degree up to n. So that for this polynomial, you take a derivative I times, then evaluate at the point ai. You want to get the point, the value bi. Such a question is always unique solvable, always have solution, and people notice, and it's easy to notice, the solution is actually linear in this piece. So we can take a basis of that solution space. In other words, just take this B to be everywhere 0 except one entry. And then you get a basis, and the one, all the smaller B are 0, only the top one is non-zero. It's not 1 because we want our polynomial to start with the P coefficient is 1. So after the scaling, you got a unique solution, which is the nth Shankar polynomial. It's in the indeterminate x, and it is depending on the interpolating point is the ai. So let's go back to parking function. This is a work with Geological and I think 20 or 20 years ago. So we find out that polynomial actually gives you how many new parking functions are there. To be more exact, to take that polynomial, take the constant coefficients, and where the interpolating point is given by the negative of that u vectors, then this is an integer number, and it's exactly how many u parking functions are there. So this it's kind of it's a little bit harder to find that the right thing, but the proof is not hard. So I'm not going to talk specifically about our argument. So what's good about it? In general, the Gamma polynomial, if you want to write down for arbitrary interpolating point, if you want to write down the formula, it's too complicated, but it has a lot of nice, I would say, analytical properties or arbitrary equations. That polynomial can be defined in a lot of different ways, like by different equations, by integration, by recurrence, by some generating function, or by they have satisfied certain type of identity, like a binomial identity. There are a lot of nice formulas available and approaches from different angles. So basically, with that correspondence, everything you can say any formula about U parking function naturally translate to something about this counting problem. So we quickly kind of recover something. Actually, none of this result is new, like at that moment, it's already proved by parking function. But just say under the theory, you can get this just form covering naturally. And also, I want to mention kind of one special thing is called the sum enumerator, which is the generating function for the sum of you give a parking function having n terms, you take the sum, looking at the distribution. So you use the generating function, and so that sum enumerator, that one in terms of hashing function, that's actually the linear growth is a complement of the linear growth of the passing function. And that one actually can be computed as a specialization of this polynomial, where ui I think is replaced by the Q number. Otherwise, it's a lot of nice formulas. So next, go back to a special case, increasing vector parking functions. Turns out, increasing vector parking function is a more familiar classical subject, well studied already, because that gets a different name of lattice path. How do you say this? Well, same pictures before. I just show example to you by this picture. Here is my right boundary. That's my vector 4, 6, 8, 10, 12. That's my vector u. I just need less 5, so 5 further. And here is the increasing vector parking function. And how do I view it? Same thing. I want to represent it by a lattice path. We're using the vertical steps and outputting vertical steps one by one, and the x coordinate 2, 5, 5, 7, 10, and connecting them by the horizontal lines to make a lattice path. Then this is a vector parking function kind of found above by this vector, meaning I can put this number, like some marks on this level. So being a vector parking function just makes my lattice path, the vector stay on the left of this forbidden point, which basically called the lattice path with the right boundary. There are a lot of results on lattice path, right? So this is a very classical subject, I guess. So kind of we just use the name lattice path with the right boundary zero up to UN. You can get a check literature, robust result on that, and a lot of tricks or combinatorial techniques developed to deal with the lattice path. So for anyone interested, I would recommend Christian Taylor's nice chapter on lattice path counting in the handbook of numerical combinatorics edited by Migotona. That has a very gentle but very clear, nice introduction on lattice path counting. Okay, so I'm not going to talk about lattice path here, but what I want to make a point is, if you're thinking of this value, how many lattice paths are there with a given right boundary, this is going to be a function depending on this UIs. Then after too much effort, you may realize the boundary, this is a polynomial in those UIs. So the question again, which polynomial? I guess the naive guess would be is a specialization of what I just have. Well, not quite right, but not far away. So this is not a specialization, but a little bit of variation of the Gamma-Rho polynomial, which what we think is something called difference Gamma-Rho polynomial. So what we do is thinking of the discrete analog of the derivative, which is the difference operator, and here I'm using the backward one, where this is the operator of a polynomial fx is fx is the difference between fx and fx minus 1. Then using this one, do the Gamma-Rho interpolation. So looking for a polynomial which, after taking the difference I times and evaluate the point of ai, you want to get say 0 everywhere, and to the last one is sum of the power. So interpolation problem, and using this operator, what we'll have is kind of similar. That Gamma-Rho, that difference Gamma-Rho polynomial, kind of corresponding to that express. You need a little bit of scaling of the factorial, but in the same way, that is the constant coefficient of that polynomial, and the interpolating point is given by negative vector. So here is what I and Joseph found out, and the natural question would be, can we repair more on our structures? So for example, can we think of that parking process, car parking, finding their spot? What happens if you say those cars belong to several different companies? They may not be all different companies, but some are coming from the same company. And you would require that cars from the same company want the same parking spot. In that case, how many parking functions? Turns out, by the idea of Gamma-Rho interpolation, you can actually answer such a question. What you do is to replace the difference of the differential operator by something called delta operator. So here I have to say the delta operator, this kind of thing belongs to a subject called the finite operator calculus, which is, I think, the algebraic theory. And this is already been in the literature for a long time, but the systematic study and the putting out was done by my advisor, Giancarlo Rota. And if you look at his famous foundation for combinatorial series, he had 2 papers devoted to this subject. Series 7 is on the algebraic setting, and the 3rd is actually on the combinatorial interpretation. So I'll just be quick. What happens is there is something called a delta operator, which is a linear operator applied to a polynomial ring, and which is supposed to be an analog of the derivative. For each delta operator, it uniquely corresponds to a sequence of polynomials, because the basic sequence of the delta, this is a polynomial which has 1 in each degree. And those polynomials are categorized by their polynomial sequences of binomial type. And the binomial type, and I'll just see what that is, but they frequently show up in binomial counting. Oh, you can think this is actually the places where we apply the exponential generating function. We want to capture the structure of something, like you have an element partitioned into several blocks and put some combinatorial structure on each block, asking how many ways you can do it. That's basically the binomial structure. Those things are elements is counted by P and X, where here X is a variable, but its power is keeping track on how many blocks are there. Then in here, then from Richard's gradual course in algebra combinatorics, we know you can understand such things as by taking X to be a positive integer. So X power is kind of giving each block a label, which is an integer from the 1 to that integer. Hence, such a polynomial right now becomes a number, which counts how many ways you can have a structure on those blocks and a function from those elements to positive integers, so that it's constant on each block. So that's where the 6 get connected. So we put these 2 things together, the delta operator and the Gamma-Rho interpolation, then having them together to create something called the delta Gamma-Rho polynomial, which I guess is the 3rd time I'm repeating. So this is the interpolation problem where the sum knows you want a polynomial. Apply the delta operator I times to it, evaluate at the i's number, then you want 0, 0, 0 everywhere until the last one. And things are always solvable, the solution is unique, and all the previous kind of nice properties in the classical case have a natural analog, since basically everything is true. I'll just have this is some computational thing I'll skip. So the major theory is that such some kind of polynomial in general enumerate the enriched parting function. So this is more precise definition. Again, we're looking at this number, the constant of that polynomial, where the interpolating nodes are given by the negative factor. So these things enumerate how many pairs of the following property is counted two components, a partition of the n elements, and there's a special structure on each block of the partition. Then you have a function mapping the elements to this capital S, which they represent the numbers 1 up to x. So you kind of mapping each element to x, that's their current preference. But this time with the property that such a preference constant on each block of time. So curve from the same company with the same spot. In that setting, you're looking for how many preference sequences is a U parking function, and that number given you by this gamma rho thing. Okay, so this is one thing. Then what else can we think along this line? So here is another possibility. So how about thinking of a higher dimensional parking function? For a long time, I was looking for what's a natural, reasonable generalization of parking function in higher dimensions. Well, there is no G parking function, but it's kind of, this is general, but it's kind of going in another direction. Thinking from this Gamma interpolation kind of suggests a way to generalize the vector version to higher dimension. So that means that what that is, right now, I'm only describing what happens on 2 dimensions, but setting up here, I'll all go through in NA finite K dimension. So 2-dimensional, we're looking for a polynomial 2-variable x, y, interpolation. So instead of a sequence of points in the 1 dimension, in the 2 dimension, I will give you like first thinking of the index is a rectangle, and in each integer point in the rectangle there is a point. So that's the point for our interpolation. So the 2-dimensional Gamma interpolation problem is we're looking for a polynomial of this joint degree at most mn, so that think the usual thing. For this polynomial, take the derivative to x I times, then the derivative to y j times. Then evaluate the point zij. You want to get whatever your prefix number. And the same as before, if you take average 0 until 1 point is the non-negative number, you get a solution. And you get a basis of the solution. And that basis is called the like 2-dimensional Gamma polynomial. So all the algebraic theory in the polynomial side, actually you can recover everything 1-dimensional, generate to 2-dimensional or higher dimensions. But just the formula, what it used to be a single summation, right now becomes a double summation, or depending on the dimension, a summation over k. So the formula are complicated, but in theory it's parallel. But what I would be more interested is what does that say in terms of combinatorics? 1 dimension, that's vector parking function. 2 dimension, what is that? It turns out this can be interpreted as something. I will call it 2-dimensional vector parking function. It defines something on integer sequences. What is exactly that? So the thing we have will be 2 sequences. One of positive non-negative integers. One is of size m, and the other is of size n. So here is our candidate. And what used to be a vector in 1 dimension, right now replaced by a grid, which is a rectangle with its horizontals and vertical steps. And each step is equipped with a weight, where the weight is basically given by, well, you will call the interpolation point zij. The x coordinate gives you the weight on the horizontal edges, and the y coordinate gives you the weight on vertical edges. So it's kind of, you put on here, this is a weighted graph, that's a test. Whenever you have a pair sequence, you feed this into test. And if you pass the test, that's a parking function. If you fail, that's not a parking function. And what is the test? Well, the wording is like something as other statistics can be found by that is passed. But let me show you my picture. Okay, so here is an example. I have a grid with 3 times 4 and there are weight on each edge. And I'm looking at this pair sequence 2, 3, 2, and this one. I'm comparing, asking whether that is a parking function defined by this is my vector U basically. Whether this is a pair of 2-dimensional vector parking function. So here's what you do first. First, rearrange each sequence from small to large and put them one on the bottom, the other on the left, comparing with my grid. Now, next, for each entry, say this 2 here, I will compare this with all the horizontal edges above this, and I will highlight those which have a weight larger than this number. So the first step, I have 3 edges highlighted. I'm doing to the next entry, compare to the things on top, highlight things with bigger weight. And same thing the next one. So I got the listings highlighted. Similarly, for the vertical entries, I will compare each entry on the left with all the vertical edges to its right and highlight those things which has a weight bigger than the entry. So the text is, after I have such a highlighted picture, asking whether one can travel through those highlighted edges from this big origin up to the diagonal entry. And in this picture, you can see, oh yes, I can travel. I can more than one way to travel from the bottom, like lower left to upper right. It doesn't matter how many ways you can travel. If you can, it's passed. So this is a 2-dimensional parking function. And if one cannot, that's not. So here is kind of a bad example. What is not a parking function? So you give us, I just adjust the numbers a little bit and give you 2 sequences. So putting them down and on the right and the left, comparing things with the weight and highlight those things from our sequence. Now in this picture, you can see, you can just do from this lower corner, you cannot go reach the top right corner by the highlighted edges. So fail. That therefore this is not a parking function. So that's the definition. I wanted to mention some special case. If in given the weight, horizontal weight only depending on their x coordinate and the vertical weight only depending their vertical coordinate, that's actually not so interesting. That's just a 2 independent sequence of 1-dimensional vector parking functions. So what's interesting is you switch kind of horizontal depending on the y coordinate and the other way. Vertical edge depending on x coordinate, which turns out the lower is the example and the simple is the example. In that case, is you have to compare the weight. That structure turns out to be coincident with a notion of PQ parking functions, which is proposed by Corey and Paulahan. Their motivation is this kind of thing is given you by the recurrent configuration of the center-tile model in complete bipartite graph with additional roots. And people permitted the G parking function of that's exactly the G parking functions, which is corresponding to a complete bipartite graph. So that's why it's actually kind of strict graphical generalization, but we can have more general. Just one more word on this one. Actually, for this case, if you look at the increasing parking function, we'll just take the 2 sequences to be weekly increasing already, so that's increasing parking function, and that will correspond to actually can be viewed as a pair of non-crossing lattice in a rectangle. So that one has a lot of that one is counted by Mariana number and have a lot of interesting combinatorics. So the final thing I want to mention is in the vector parking function, the nicest form is when you have the vector is arithmetic progression, which we have a lot of nice realization. And just computationally, in the general higher dimensions, if the weight is arbitrary, then it's it's hard to compute. But there is the K case, which we call a fun case, where the weight is given by kind of linear transformation on the coordinate. So that is the case. We have nice formulas, and right now we are just still investigating the relations or maybe applications to other combinatorial structures. So as the content I want to say, and I really want to finish this one with a comment that I feel really fortunate to went to MIT, so I can work with these two great, I think actually two greatest combinatorists, Giancarlo Rota and Richard Stanley. And I was able to using what they taught me and having this nice project applying the both theory, and which gave me many years of fun and pleasure. So thank you, Richard. I'm happy with you.